Jai Hind everyone. I am Dr. Prashant Tripathi, Assistant Professor at Akgec Engineering College in Electronics and Communication Engineering Department, going to present a lecture on information theory. This lecture is aimed for BTech 6th semester student who are reading Digital Communication KEC 601 paper. In this presentation, we will discuss about information theory, what is information, how can we measure information, what is the average information of a source, and how it depends upon the probability of occurrence of symbols. So, first of all, we will discuss about uncertainty and measure of information. In digital communication, we have discrete information source. Discrete information source means the source which generates discrete symbols with a finite probability. Like when we throw a dice, we have 6 outcomes which are 1, 2, 3, 4, 5 and 6. Apart from these 6 outcomes, we have no any other outcome. So, this is an example of a discrete source. Similarly, our computer keyboard is also an example of discrete information source in which each symbol generates with a certain probability. In this case, before any event occurs, we have uncertainty about the outcome of that event. When the event occurs, we have, on observing the output, we gain some information and we can say that the following event has occurred. So, when we talk about information, we will see that the information is directly inversely proportional to probability of occurrence. For example, if I say the sun rises in the east, there is no gain in information because this is in universal truth and the probability of this event is 1. So, in this way we can say that the probability directly influences the information. If the probability of occurrence of a symbol is lower, we have more gain in information. But if the probability is higher, we have lesser amount of information. For example, if probability of occurrence of a symbol, no uncertainty in the source and we have no gain in information. Also, when we take other extreme case, that is pk equals to 0, this is an hypothetical event and if this event occur, we have an infinite amount of gain in the information. So, we can say that the probability of occurrence is inversely proportional to information. The information corresponding to a symbol xk is equal to log 1 by pk, where pk is the probability of occurrence of symbol xk. We can write this formula in this way and the unit of this log may be vary. If the unit of log is 2, then the information unit is bits, and if the base of log is e, it is known as nuts, and if the base of log is 10, it is known as heartlays. So, depending upon the application, we have different base for the log. Mostly in our digital communication, in binary transmission, we uses the base as 2. So, the unit of information is bits. And to calculate the information, it is clear now that we have to take the log of probability of occurrence of a symbol. Now, we will see how we can calculate the information associated with the symbols. In this example, we have a source which emits four possible symbols which are x1, x2, x3 and x4 with probability of 1 by 2, 1 by 4, 1 by 8. Now, we want to compute the information content of each source symbol. To calculate the information associated with each symbol, we can use the formula I information associated with symbol x1 equals to log at base 2 1 by probability of x1, which is equals to log at base 2 1 upon 1 by 2, and it is simply log 2, which is 1 bit. Similarly, information associated with symbol x2 equals to log 1 by probability of symbol x2, which is log at base 2 1 by 1 by 4 log 2 bits. Information associated with x3 equals to log 1 by 1 by 8. This is equals to 8 and this is 3 bits. Since the probability of occurrence of symbol x3 and x4 is same, we can directly write that Ix4 information corresponding to symbol x4 will be equal to 3 bits. So, in this way, we can compute the information content of each symbols. Now, we will talk about entropy. The entropy is related with a source and it represents the average information content of a source. The entropy of a source is defined as Hx equals to summation Pk into log 1 by Pk. In this way, we can compute the average information of a source. The entropy has three properties. For a random source that generates k discrete symbols, the entropy has following properties. First property is the entropy is bounded with 0 to log k, where k represents the number of symbols. Hx equals to 0 if and only if pk equals to 1 and pi equals to 0 when I is not equal to k, and the maximum value of Hx is log k if and only if the symbols are equiprobable, and in this case the probability of each symbol will be 1 by k. So, we will now see the proof of the first property of entropy. Suppose we have a random source which generates we have two random source x and y which generates k symbols with probabilities of pk and qk. For example, the source x1, the source x generate symbols like x1, x2, x3 and so on with probability p1, p2, p3 and so on. Similarly, source y generates symbols y1, y2, so on with probability q1, q2 and so on. In this condition, we can write that summation over k, where k varies from 1 to capital K, Pk log Qk by Pk at base 2 in this way. Now, using the log identity, we can decompose this expression into this two part, Pk log Qk minus Pk log Pk. Now, we are using simple log identity that ln x is less than or equal to x minus 1. So, when we apply this identity, we can write that this this quantity must be less than or equal to Pk Qk minus Qk upon Pk minus 1 into log E. Here we have converted this log at base 2 into natural log. Now, when we solve this equation, we will find that this convert into this form Qk minus Pk into log E, and this quantity it must be equal to 0, because when we operate the summation sign, we have summation of Qk where k varies from 1 to capital K into log E minus summation of k varies from 1 to k log E into Pk. So, this whole quantity is 1. We can say log E at common 1 minus 1, and this is equals to 0. So, we have find that this quantity is less than or equal to 0. Now, this quantity is representing the entropy of source x. So, we can write this quantity as Hx, and this must be less than or equal to minus of Pk log Qk. For example, if we assume that in source y all the symbols are equiprobable, in that case the probability of occurrence will be 1 by k. So, if we put 1 by Qk, if we put 1 by k in place of Qk, we have this equation, and after solving we can find that this is log 1 by k summation over k, where k varies from 1 to k Pk, and this quantity is 1. So, we have minus of minus log k, and we have this quantity is must be less than log k. So, we have proved that the entropy is bounded with two limits 0 and log k when the symbols are equiprobable. Now, we will derive an expression for entropy function in which we have a binary memoryless source which emits two symbol x1 and x2, and we will prove that entropy is maximum when x1 and x2 are equiprobable. So, we are going to assume that the probability of one symbol x1 is p, then the probability of other symbol will be 1 minus p. So, entropy of this source will be k varies from 1 to 2 Pk log 1 upon Pk. We can write P1 log P1 minus plus P2 log this is equals to minus P log P plus 1 minus P log 1 minus P. Now, to find the maximum value of entropy, we will differentiate this entropy with respect to P, and we will find P into 1 upon P plus log P plus 1 minus P into 1 minus P here we have log E log E and minus 1 plus log 1 minus P. Now we have minus log E minus log P plus log E minus log 1 minus P. This equation will get cancelled. We have minus of log P minus log 1 minus P. This can be written as now log P minus, just here we have one more minus, so it will be minus, this will be plus. So minus log P plus log 1 minus P, this will be minus, equals to 0. When d by dp of Hx equals to 0, we can write this equation. Now, this equation can be written as 1 minus P by P equals to 0, and we can write this as a log 1. 1 minus P by P equals to 1. 1 minus P equals to P, and 2P equals to 1 and P equals to half. So, we have proved that in case of equiprobable symbol, we have maximum entropy, and for this maximum entropy, in this case, the probability of occurrence of symbol must be equal to 1 by 2. So, in this case, we have proved that if the symbols are equiprobable, it means their occurrence probabilities are equal, then only we can get the maximum entropy, and in this case the entropy will be log of number of symbols, which we have derived earlier, and this is log k at base 2. Thank you. These are the two references which I have used for preparation of this content.